freely falling bodies is going to be the topic of this lesson in my brand new general physics playlist. So in the last lesson, we started doing calculations involving kinematics in one dimension. And in this lesson, we're going to introduce gravity, which is our most common source of uniform acceleration in one dimension. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, for the next few questions, we've got to talk about free fall and gravity. So it turns out that there's a good chance you are familiar with gravity, even though you probably don't have much of a clue of what it is. And I'm in the same boat. I don't really know exactly what gravity is. I know they've talked about gravitational fields and waves and all this stuff lately in the news and things of this sort. And again, I feel like I have an intuitive feel for gravity. I experience it every day and stuff like this. But what is it? What is it that makes that, two objects that both have mass be attracted to each other? I don't know. And my experience of it on the surface of planet Earth might be totally different than, the experience out in space and, or between two planets or, all that kind of thing. So we think we have a pretty good handle on what gravity is. And the truth is, even our mathematical equations we're going to use for gravity in physics, they're really just descriptions of how gravity behaves, not so much a definition of what gravity is. So just keep that in mind. But gravity is an attraction between bodies with mass. And on the surface of the Earth, it's just a force that attracts things toward the Earth. That's what it does. And as long as you're near the surface of the Earth, it turns out there's an acceleration associated with gravity that's fairly constant. And that acceleration due to gravity is equal to 9.8 meters per second squared. Now, the truth is it does vary a little bit. And the truth is, the higher you go up in altitude above the Earth, it does go down a little bit if you get too far above the surface of the Earth. However, there's a pretty big range, near the surface of the Earth, at which that's a really good approximation, and the one we're going to use throughout this course, 9.8 meters per second, which I like to round to 10 a whole lot in my head when I'm doing sample calculations to get a ballpark and see if answers make sense and things of the sort. Now, some people like to put a big fat negative sign on this because it points down. And it's really customary for problems that involve the y direction, the up-down direction. To make going up the positive direction and going down the negative direction. And great, I'm okay with that as well. And the key here is that when you're doing kinematics calculations, if your displacement, your velocity, and your acceleration all point in the same direction, all up, all down, then your signs don't matter. You can make them all positive, you can make them all negative. If they all point up, customary would be to make them all positive. If they point all down, customary it would be to make them all negative. But in either one of those cases, even if you did the opposite, no matter how you use the equations, the math would work out the same to give you the same answer. However, if your acceleration, velocity, and displacement point in different directions, any one of those three points in a different direction than the other two, your signs are going to matter. And what you make positive and what you make negative is going to be super important. All right, so now that we've got that underway, now one thing to note is notice I've told you the acceleration due to gravity, and I didn't have to tell you what the object was. I didn't say, what's the acceleration due to gravity for a rock? It's 9.8 meters per second squared down towards the Earth. What is it for a feather? It's 9.8 meters per second squared down toward the Earth. But our experience says, no, the accelerations for a rock and a feather are not the same. Well, it turns out the feather experiences a whole lot more air resistance than the rock does. And so it has a counterbalancing force pulling it, dragging it back up, if you will, providing drag against gravity. But if you did this on the moon, you could drop that rock and that feather and they would fall together if you dropped them at the same time all the way to the moon because there's no air there. If you drop them inside a vacuum, same thing. And that's a weird thing, right? And if we go a step bigger with, instead of rock, let's go bowling ball. Bowling ball and feather, they would fall together on the surface of the moon. Now, it turns out the gravity on the surface of the moon is not equal to this number right here. It's about 6 times smaller. But it would still be equal for both the bowling ball and the feather, and they would fall together. That wasn't supposed to rhyme. All right, so now that we kind of got a good idea what gravity is, this is a number you're supposed to know. When you're dealing with free fall calculations like we're about to, or anything involving gravity, this is a number that question writers are going to anticipate that you have in your head. All right, so here we've got a stone is dropped from a great height and takes 4 seconds to reach the ground. From what height was the stone dropped? Ignore air resistance. Okay, so it's dropped a stone from a great height. And it takes 4 seconds to reach the ground. From what height was the stone dropped? Ignore air resistance. Okay, so there's a couple different approaches we can do here. So one thing you should note is that when we want to know what's this original height, essentially what we can do is just say, well, the height is equal to the magnitude of the displacement that it falls. So that's one way to look at it. So, and ultimately the ideal way to look at it. Now, one thing to note is that technically some people say, well, the displacement is in the downward direction, so that would technically be a negative number, but the original height of the stone is a positive number. Well, okay, great. So, but it turns out also this, which way does acceleration of gravity point for this stone? Down. Which way is its velocity the entire time through the motion after it's, dropped from a velocity of 0? Down. Which way is its displacement? Down. Well, because the acceleration, the velocity, and the displacement all point down, you can make them all positive, you can make them all negative. It doesn't matter. And so I like making things all positive when it doesn't matter, so which is kind of customary. And so when I solve for the displacement, it comes out positive, that will be equal to the height of that stone. Okay, now a couple things we can reason out just by looking at this. Again, there's my acceleration due to gravity, which again, I like looking at differently unit-wise and just saying it's equal to negative 9.8 meters per second, which notice that's approximately 10 meters per second, or negative 10 meters per second, or 10 meters per second downward. And so that means when something is dropping towards the earth, it's accelerating, as long as we get to ignore air resistance anyways, at an acceleration of 10 meters per second towards the earth. So if this thing's dropped from rest, then its initial velocity is 0, but 1 second later, its velocity will have increased by 10 meters per second. Again, it's 10 meters per second. And so after 1 second, it'll be a velocity of 10 meters per second. After 2 seconds, it'll speed up and now be up to a velocity of 20 meters per second. After 3 seconds, it'll have sped up and its velocity would now be 30 meters per second. After 4 seconds, it will have sped up and its velocity would now be 40 meters per second. Well, that's our 4-second journey. So one thing I can say is that the initial velocity is 0 and the final velocity is approximately 40 meters per second. Now, it's not exactly, because I'm saying if we use that nice, lovely rounded number to 10, if I use 9 point out, it's going to be a little bit less. But I can really easily, understanding what acceleration means, get the initial and final velocity and say, does that help me? Well, yeah, it kind of does, actually, because I can find the displacement pretty easily if I have the initial and final velocity and can get that average velocity and go from there. In fact, we can do this in our head. What's the average of 0 and 40? Well, the average velocity is therefore 20 meters per second. 0 plus 40 over 2, or halfway in between 0 and 40. That's 20 meters per second. How long is the whole journey? 4 seconds. Oh, well, problem done, right? We can say that delta x equals v average t. Delta x equals 20 meters per second, that average between 0 and 40, times the total journey of 4 seconds. And it's going to be right around 80 meters. Now, one thing I should do is, since I use approximate numbers here, then I should use approximation signs here. But when we solve for this, it should be around 80 meters, and maybe just a little bit less since our average, since this final velocity is a little less than 40, our average is going to be a little less than 20, which means our displacement is going to be a little less than 80 meters. But now we've really quickly done a lot of the math in our head and have a really good approximation so that when we do finally calculate the exact answer, we know how to ballpark it and know if it makes sense. Cool, that's not the only way to do this one. So we can also use this next equation here because we have the initial velocity 0, we have time, 4 seconds, we have the acceleration and time again. So, and that's not a bad calculation to go either. Truthfully told, it's not really any much harder than this one. So v initial t plus 1/2 a t squared. So delta x, what we're solving for. And what's nice is that as long as you start with initial velocity of 0, which is really common, this whole first term goes away because initial velocity is 0 and anything times 0 is 0. And so we're just left with 1/2. So and in this case, 9.8 meters per second squared times 4 seconds squared. You might be like, Chad, it's negative. It is, and I don't care. And again, whether I make the displacement, the velocity, and the acceleration all positive or all negative, because they all point in the same direction, so I'm just going to leave them all positive. That's my choice. Pretty customary. It's, again, your signs are going to be really important, though, if some point up and some point down, which we'll see in other problems. All right, so in this case, and notice we could ballpark this in our head as well. So here's 4 squared is 16. 16 times about 10 would be 160, times a half would be 80, and we get roughly the same answer. We'll let our calculator do all the math for us here. So 4 squared times 9.8 times 0.5 gets us 78.4 meters. By the way, I meant to say this earlier. So in laying the conceptual foundation for a lot of these calculations, I'm using numbers that are easy to work with on purpose so we don't get lost in the math. And I'm also completely not worrying about sig figs. So, and as I said back in chapter 1, sig figs are super important for physics, but I don't want to lose the forest through the trees as we're gaining this conceptual understanding. So I'm using nice numbers and ignoring sig figs. It is important. There's just something more important going on in this lesson. All right, so displacement of 78.4 meters, that is the height from which the stone was dropped. All right, so we're still dealing with a stone being dropped, and this time we're told that it's being dropped from a height of 100 meters. Okay. How long does it take for the stone to reach the ground? Ignore air resistance. So now it's being dropped from a height of 100 meters, and how long does it take to reach the ground? Well, comparing to the last problem, so we found it was dropped roughly from a height of 80 meters, and it took 4 seconds. So if this is 100 meters, well, only because we have that comparison, we could say it's going to be a little longer than 4 seconds. So, but that's only because we had that. That's, we haven't got anything universally figured out here. It's only by comparison of the problem we just did. But how do we actually figure this out? Because the same thing's true here. We still got gravity with a acceleration of roughly 10 meters per second. So I can calculate velocities all along the way, but this is not a velocity, it's a displacement in meters. And that's not going to, help me too much. Now I could, try and figure out, well, how long does it travel in the first second, and then the second, and third second? We could approach that, but that would be super lengthy in our calculation and not a great systematic way to approach this and stuff like this. But the key is this: I don't have any way to know the final velocity. I know what the initial velocity is. I don't have a great way of calculating out that final velocity this time like we have in other problems. And so this first equation, delta x equals v average t, it's not going to be super helpful this time around. Okay, well, let's look at what we know. So we know the displacement is going to be down 100 meters for it falling to the ground. Okay, so we know displacement. So we want to know time. We want to solve for t. Okay, so, and we know the acceleration. And it makes it look like this equation might be a good one because we've got the displacement, the initial velocity is 0. So in the acceleration and stuff like this, it looks great. Now here's the deal though. The only reason this is going to end up being a great equation to use is because the initial velocity is 0. So had there been an actual initial velocity, then this term wouldn't go away, and you'd have a t and a t squared, and we'd have to solve a quadratic, which I dread. So in almost every case I can think of, I can avoid using the quadratic by using some other combination of these lovely equations. So, but in this case, we don't have to worry about that. So because the initial velocity is 0, it's being dropped from rest, and that term's going to go away, and that'll work. So delta x equals v initial t plus 1/2 a t squared. And again, that initial velocity is 0, so that term disappears. And from here, delta x is 100 meters. It's equal to 1/2. Acceleration is 9.8 meters per second. And then times t squared. And in this case, no quadratic, we'll just have to take a square root. And again, you might be like, wait a minute, Chad. What about negative and stuff like that? Once again, the displacement is technically negative 100 meters, and the acceleration is technically negative 9.8 meters per second. But whether I make both these negative, those negatives cancel, and so leaving them both positive works. And again, the key, if your displacement, your velocity, and your acceleration all point either all up or all down, then you can make all those terms positive, you can make them all negative, it is your choice. It'll work out the same mathematically either way. All right, so in this case, we're going to get t squared equal to 2 times 100 meters. all over 9.8 meters per second squared. And we'll let our calculator do the math for us here, but you could probably approximate this in your head. 2 times 100 is 200, divided by 10 is roughly 20, and so we're at t squared equals 20. We'll take the square root, and square root of 16 is 4, square root of 25 is 5, so square root of 20 is somewhere in between 4 and 5, and it's a little longer than 4 seconds, just like we said it should be. All right, 2 times 100 divided by 9.8, and then that's 20.408, and we'll take the square root. And we're going to get 4.5, 2 seconds, I'll round that to 4.5. And that comes out in seconds. And notice we do the math here, so the meters here are going to cancel, and you got 1 over second squared, and that's divided by, so it ends up being second squared, and we take the square root, it comes out in seconds. So one nice thing again is if you use SI units religiously, so the units just kind of work out. And you can verify it every time, and I highly recommend you do, but the units will just kind of work out if you've done all your math correctly. All right, last question involving free fall, and we're dropping a stone from rest again. And so here it says a stone is dropped from a great height. Its final velocity just before it reaches the ground is 60 meters per second. From what height was the stone dropped? Ignore air resistance. Okay, so now we want to know what that height is. And so here, we don't know. What we do know is that the final velocity, right as it's hitting the ground, is 60 meters per second. It's dropped from rest, so the initial velocity is 0. So we know the initial and final velocity, and notice you can probably rationalize some things out here and be like, oh, the acceleration due to gravity is approximately 10 meters per second every second. So to go from 0 to 60 meters per second, well, again, after 1 second, the velocity would be up to 10 meters per second downward. After 2 seconds, it'd be up to 20 meters per second downward. After 3 seconds, it'd be up to 30 meters per second downward. And maybe you can see that it would take up to the 6 second mark to get a velocity of 60 meters per second. Okay, so from 0 to 60, it's going to take us 6 seconds. So that means it takes 6 seconds to reach the ground. But notice also, if we're going from 0 to 60, that means the average velocity is 30 meters per second. And the journey is 6 seconds. And we've already very quickly deduced how to calculate out the displacement, which is the height from which that stone is dropped. And so in this case, in approximating it, we got delta x, and that average velocity, again, is 30 meters per second, just the average of 0 and 60, halfway in between is 30. So, and then the total time, 6 seconds. And so delta x should be approximately in the ballpark of 180 meters. And again, we have to say approximately because we were assuming a value for gravity of 10 meters per second instead of 9.8 meters per second. But when we solve for this exactly, it should be in the ballpark of 180 meters. Cool. And that's one approach we could take. So if we look at what we've got, again, we're given the initial velocity and the final velocity. So, and we want to know the height. We were not told anything about the time it takes. Now we figured it out, and technically you may not have realized it, to go from 0 to 60 and figure out it takes 6 seconds. We were technically using that equation right there without realizing we were even using an equation, hopefully, but you could always definitely plug and chug it with that equation. So, and in doing that, we figured out the time of roughly 6 seconds. And so even though we weren't given the time, we could figure it out pretty quickly and avoid using this equation. This is the big equation where if you don't know anything about time, but notice we do know the initial velocity was 0. We do know the final velocity was 60 meters per second. We know the acceleration, and we could solve for the displacement. But we can get around it as well. We're going to solve it both ways, though. All right, so let's do this exactly now. So in this case, we could say that your final velocity equals your initial velocity plus AT, and solve for time. So final velocity is 60 meters per second. Initial velocity was 0. Acceleration due to gravity is 9.8 meters per second times your time. And in this case, we'll just take 60 over 9.8. Instead of 60 over 10 to get 6 seconds, it's 60 over 9.8 to get something just slightly larger. So 6.12 seconds. So now that we know that, we could use either one of these equations and plug in the time and go from there. Well, I like that top one. Average, again, between 0 and 60 is 0 plus 60 over 2, or 30 meters per second, times a time of 6.12 seconds. And again, we had already ballparked this out at roughly 180 meters. We see it's going to be a little bit higher. Take my last answer times 30, and it's going to come out to roughly 184 meters. A little bit bigger than what we calculated, since gravity is a little bit smaller than 10 at 9.8 meters per second squared. Cool. Again, we could have also used this lovely equation from there and just done 1/2 times the acceleration due to gravity of 9.8 times the 6.12 seconds squared and got exactly the same answer. Or we could have just never bothered to calculate out the time and just used this equation instead. And then had we done that, v final squared equals v initial squared plus 2 times a times the displacement. Final velocity was given as 60 meters per second. We'll square that. Initial velocity was 0. And so 2 acceleration due to gravity is 9.8 meters per second squared times your delta x, and solve it from there. So here we take 60 squared and then divide it by 2 times 9.8. Cool, and when you do this in your calculator, if you're dividing by 2 times 9.8, make sure you put 2 times 9.8 all in parentheses. Whereas for me, I'm doing 60 squared over 2 over 9.8, so I don't have to put it in parentheses. But same diff, and it still comes out to roughly 184 meters any way you slice it. So more than one way to skin a cat. So hopefully we've given you a little bit of an intuitive understanding of what acceleration is and how we often can use it to find the final velocity and get an average velocity, which makes this equation really convenient when we've got uniform acceleration. So hopefully you realize, kind of first question is, do I have acceleration, yes or no? If there's no acceleration, i.e. we're at constant velocity, only equation we got. If we do have uniform acceleration, and gravity is a really common example of that, so then I've only really got 4 equations I have to work with. One of them conspicuously doesn't have time in it, but oftentimes there's a way to get around it because I hate using that equation. Squaring numbers often makes numbers get big in a hurry, and I love doing these in my head, preferably, or at least ballpark in my head, and that one is tough to do sometimes, but sometimes it actually is the most convenient, especially if you're doing something with a calculator. So, but even if you don't have the greatest handle on this, sometimes it's nice to just start trying these equations in order, or at the very least looking at what quantities do I have and how do those quantities fit into these equations. And what you'll find is that even just systematically working through them, you're going to start to get a feel of when a certain equation is appropriate versus another. And as I also pointed out, oftentimes there's more than one of these equations that you can use to solve a problem. And sometimes you could use any of those equations to solve, or at least some combination of any of those to solve a problem as well. Cool. If you have benefited from this video and you've liked this lesson, then please like the video as well. Happy studying.